So by looking at addition, subtraction, we start to see this idea that there are positive and negative numbers, of course, in binary as there is in decimal. But one of the problems that we haven't approached yet is how do we even represent these signed numbers, right? And that's what we're going to approach in this video. And there are three main approaches that we're going to discuss, and one of them is really the main one that we're going to see used, and we'll take a look at how that actually gets represented by taking a look at some actual live C programs in the video after this. So let's discuss the general theory, then we'll take a look at it actually in practice. The idea of negative numbers is that there are really three main approaches that we would typically see used. The first is going to be what is known as a signed magnitude, the second is a ones complement, and then the third is a twos complement. So let's start by discussing the idea of assigned magnitude. With assigned magnitude, what we do is we say that the most significant bit, or the leftmost bit in a binary number, indicates its sign, either a 0 for a positive number or a 1 for a negative number. So for example, the following binary number here would be representative of -6. The reason being is that we have 4 plus 2, which is 6. And this leftmost bit indicates the sign. Because it's equal to 1, it must be a negative number rather than a positive number. This sort of system seems like it would work pretty well, right? But there are a few problems that exist with it. The first problem is that when we take a look at any two numbers and we want to do some operations on them, we have to understand the signs of those numbers. So if both of the numbers have the same sign, for instance, and we try to add them together, that would be okay, right? We would be able to do that and we would preserve the sign bit. There'd be no sorts of problems. However, if they had different signs, we had a positive and a negative number, and we tried to add them together, we would have to subtract instead. So we have to think about the different situations that we may encounter, which is not really ideal, especially when we're working with circuitry. We want it to be a bit more easy to work with. The other problem that we run into here is maybe a little bit less obvious, but it's the fact that we actually have two representations of the number 0 in this system. You'll see here that this is 0 and this is also 0, right? Technically -0 and +0. This is not ideal, and the reason why it's not ideal is because if we wanted to check if something's 0, we would have to do two different checks, which is not something that we want to do. We only want to have one check and therefore 1, 0. So this approach seems okay, but it's not quite what we're looking for. So we'll move to something a little bit different, and the first idea would be what's known as a ones complement. The idea of a ones complement actually comes from decimal values. So in decimal numbers, we could do a really interesting trick with negative numbers. Let me give you an example. Suppose that you wanted to figure out 120 minus 60. What you can do is you could take the 60 and you can subtract it from 999. What that would give you is 939. You can then take the original number 120 and you can add it to 939. The result that you would get is 1059. And then what you do is you take anything beyond the number of digits that we have in both of our operands. In this case, they're both 3 digits. So we take the thing that is the fourth digit, we add it back on. We treat it as a carry, essentially. That gives us 060, which is the result of subtracting these two numbers from each other. We call this a nines complement, or a diminished radix complement. And the idea of doing this really comes down to the fact that rather than doing subtraction, it allows us to always do addition and still get results of subtraction. So we get one operation that is able to accommodate our subtraction without us needing to actually do a subtraction. Now in this example here, you'll see that, of course, we still have to do some subtraction. We have to subtract 999 from 60. However, in binary, this actually becomes way, way easier and therefore becomes a pretty ideal approach to handling negative numbers. So the idea in binary is that rather than subtracting all nines, we subtract all ones. So for example, if you had the number, we could say 6 as an example, right? If we have the number 6 as our number, we could subtract all ones from it. And what that would give us is the ones complement in this case, which is this. And what you'll notice here, if you do a few different examples, is that the ones complement is actually just the result of flipping every single bit in our original number. So if it were a 0, it becomes a 1. If it were a 1, it becomes a 0. So for 0, 1, 1, 0, we simply just flip our bits. This one becomes a 1, this one becomes a 0, this one becomes a 0, this one becomes a 1. So actually, we don't need to do subtraction at all. We can simply just flip the bits in our number, and we end up with the complement. This is really advantageous because it allows us to just add numbers together always. Basically, every negative number gets represented as a ones complement, every positive number gets represented as itself, and then we can add those results together in order to achieve negative signed numbers. So let me show you an example of this before we discuss some of the different things that we may want to consider with this. So for example, suppose that I wanted to do something maybe a little bit simpler, say 10 and -6. I want to represent these two numbers. In one's complement form, positive numbers stay the same. So 10 would be this, right? 8 plus 2 gives us 10, right? To represent -6, we start by representing the positive version, which is 6, and then we flip all of the bits. So the zeros become ones and the ones become zeros. This is the ones complement version. Now let me show you, if I were to take 10 in this case, and I were to add it to -6, what would we get as a result? We get 1, 1, 0, and then we have a 0 with a carry of 1. This gives us a result of 3 in this case, right? What we have to do is we have to take this carry and we actually have to add it back on like we did with the 9's complement, right? So you see what ends up happening is when you add that back on, you end up with the proper result of 4, right? So you can see that does work the same way as the 9's complement that we just discussed. And with this, we're able to just apply addition, even though this was a negative and this was a positive. In signed complement, we would have had to have accounted for that and done a subtraction between the two numbers instead. So we can see that this gives us a bit of an easier way of doing this, but there is still a problem here, and that's that we have to account for this carry. It's the first problem. The second problem is that we do actually still have two representations of 0, and they're the same two representations of 0 as before. So we're not quite there. We're not quite at the solution, but we're very close. The solution actually for this that most people use is a 2's complement. A 2's complement makes one small modification to the 1's complement. It takes the 1's complement and it adds 1 to it. So before, to represent -6, we took our 1's complement, right, to get us here. The 2's complement, we just add 1 to it. That gives us the following value in this case. Now, how does this change? Let's do the exact same operation again, right? We had the number 10, and then we have our representation of -6, right? When we add these two numbers together, what we end up with is 0, 0 carry the 1, 1, 0 carry the 1. We no longer care about this carry. We don't have to worry about adding it back on because you see that we actually ended up with the correct result immediately, right? We got the correct result of 4. This is basically because we preemptively have added the 1, right? So because we've preemptively added that, we don't have to worry about adding that carry again. So this gives us a really easy way of being able to deal with signed numbers. And then the other benefit of this is that we do only have one representation of 0, which is just all zeros. So this one checks all of the boxes. This is exactly what we are looking for. So what I'll do here is I'll show you one more example of a 2's complement. And then in the next video, I'm going to show you this actually in C, just to show you that we do actually use a 2's complement when we're looking at the low level of assembly. So with that being said, let's take a look at one more example. So in this case, I'm going to show you the following. Let's say that I want to take 14 and I want to add it to -14, right? That's what I want to do here. So first off, we need to represent 14 in binary, right? So that's going to be our first step. So the idea here would be that we would have 8 plus 4, which would give us 12, right? And then from here, we just add a 1 here in order to get us to 14, right? So this is 14. Now, in order to get the 2's complement of 14, to get -14, we take this number, we reverse the 1's and 0's, we then add 1 to that in order to give us this result. Now the question is, what happens when we add these two numbers together, right? When we do this, we get 0, 0 carry the 1, 0 carry the 1, 0 carry the 1. We don't care about that carry. This gives us our final result of 0. So you see that if I take a number and I add it to its negation, I get 0 back as a result. So it actually preserves that property of subtraction in our decimal numbering system as well. So this is a really nice property that we have available for us in 2's complement. So this gives you an intuition towards how we represent signed numbers. So we saw the idea of signed magnitude, 1's complement, and 2's complement. In the next video, I'm going to show you how this actually looks in programming so you can see how a 2's complement is actually used and what that actually looks like when we're taking a look at the lower level assembly. So thanks so much for watching this video, and I'll see you in the next one.